Okay. Hello, everyone. This is the first of hopefully only 3 videos for Monday, but also contains questions for your quiz for this week that will be due on Wednesday when I come back. Whatever that Wednesday would be, March the 4th. Okay, so that's when this is due in class. The quiz will be due. So make sure you take good notes and listen up, and I'm gonna post the quiz questions in between the videos, so you actually have to listen to the video to get all the quiz questions. Yes, I know. Lovely. Okay, so first, and if you want, and the beauty about having the video is that you can pause and go back and, re-listen to stuff. So if you want, you can pause the video now and write down this generalized principle of mathematical induction, and then we're going to start this proof. So just to make sure you understand my writing, the generalized principle of mathematical induction. And this is basically, it's really similar to the PMI. The only difference is now, with the PMI, we assume that 1 was the first element, 1 belonged in our set, which meant it encompassed the entire natural numbers because of the inductive property. However, with the generalized principle of mathematical induction, it says, okay, we're starting at some value k. That's a natural number, but we're not necessarily starting at 1, because if we started at another number, then 1 doesn't have to be in our set, and we can still conduct induction on it, just making sure we stipulate that we're just starting at a different number. Okay, so this principle says, and the structure is really similar as well to PMI. Let K belong to the naturals, and let S be a subset of the naturals with 2 properties. 1, K belongs in S, and 2 for all n in the naturals, with n being greater than or equal to K. If n belongs to the set, then n plus 1 belongs to the set. And therefore we can conclude S contains all natural numbers greater than or equal to K. Greater than or equal to K. That's what that's representing. Okay. All right, so now let's start this proof. And so during the presentations today, you notice that we use different variables instead of just n. Some used, I think, m and k and different variables. And 2 things. One, the reason why, and with this generalized principle, and in my example that I'm going to do, we're going to use k. You can actually still use n and just stick with n as long as you clearly specify that you're not including all natural numbers. And so a lot of times, or a lot of reasons why students like to deal with k instead of n, I think that's how I learned it, is because with k, you're not assuming that you're using, or your inductive set contains all the natural numbers. With n, that's sort of, n is sort of the PMI, where we're assuming 1 is in there, therefore it's all the natural numbers. That's what we want to prove. So that's just really why we switch between variables. But if you're comfortable using n, as long as I can clearly see that you're starting from a different variable, that's fine. And as you can see in this proof, it's actually in terms of n, but we're going to prove it using k's, okay? All right, so let's start this proof, and I'm going to have to go on the next page, so make sure you follow along. Well, first we're going to let S, and this is also you can also use this in terms of P of n, so if you like to use P of n instead of S, you can do the same proof using P of n, okay? So, but this is what was in your book, so I sort of wanted to do an example using it in this format. So let S be the set, n belongs to the naturals, and n is greater than or equal to 5, such that, I hope this can all fill on this line, n plus 1 factorial is greater than 2 to the n plus 3. Okay. And of course we start with our base step. And if you want to write base step, you can. It doesn't matter. This time, our property says let k be an S. And since we're starting from n being greater than or equal to 5, then for our base step, our first value is going to be 5. Okay. So we're going to let k equal 5. Well, if we let k equal 5, then the left-hand side, and I'll talk I'll mention too, hopefully I won't forget in this video, but I'll definitely mention about what I talked about in class in terms of the left-hand side and the right-hand side for the actual proof. But for now, for the base step, for the left-hand side, we have 5 plus 1 factorial, which equals 6 factorial. And if you use your handy dandy calculator to figure that out, that's 6 times 5 times 4 times 3 times 2 times 1. You should get 720. And 2, I'm sorry. So now the right hand side, and hopefully this often on this page, is 2 to the n plus 3, so 5 plus 3, which is 2 to the 8, which is, I believe, 256. Okay, so we can say hence 720 is greater than 256. And I would definitely put this on the line underneath, but because I don't have the space on here, the line underneath that should say, thus, 5 belongs in S. So we just showed that 5 belongs to our set S, and we're now done with our base step. So I'm going to go to the next page, and we'll start our inductive step. Okay, so now we're on to our inductive step. And again, you might want to pause and write down, and then and then press play again to listen to the proof. So here we're assuming this is where we change our variables. But again, if you want to keep n, you really can keep n. It's not a big difference as long as I clearly see that your n is greater than or equal to 5. Okay. All right. So suppose k belongs to our set S. Well, according to our definition of our set, that means that we already assumed that k is in a natural number and k is greater than or equal to 5. So that the remainder of that would just be k plus 1 factorial is greater than k plus 3 factorial. Okay, so we want to show that k plus 1 belongs to S. Well, what does that mean? So now again, that's why I prefer using P of n instead of S when I'm doing induction, but it's really up to you. So thinking about it as a function, wherever you see a k, you're going to plug in k plus 1. So that means k plus 1 is greater, k plus 1 factorial is greater than 2 to the k plus 1 plus 3. Well, simplifying that, that just means k plus 2 factorial is greater than 2 to the k plus 4. Okay, I had to squeeze it in there, so hopefully you understand that's 2, all that to the k plus 4 that's in our exponent. So that's what we need to show, okay? And we always sort of start, even though this isn't an equal sign, it's not an equality. Well, it's an inequality, but it's not an equal sign. It's not an equality. We still can start with the left-hand side. Sometimes you start with the right-hand side. So this is the point I want to make. When you're doing a proof, you usually start with the left-hand side. If you get stuck sometimes, so if you get doing some algebra and you get stuck, sometimes you can also work from the right hand side and show that those two are the same. Okay, so that's a proper structure too, but I want you to know the formal structure of it first before you try to, do shortcuts, because I want to make sure you understand the formal structure of an induction proof. So that's also, it's legal. But just make sure you understand and careful with that, because you don't want to assume things. Sometimes you can assume what you're trying to prove, and that's where you can get confused. Okay, so back to this proof. We're starting with the left. So k plus 2 factorial. Well, that equals, remember, you always want to think about your inductive hypothesis, right? So that equals, if we can actually break this down by the definition of induction, k plus 2 times k plus 1 factorial. All right. And now right here, I'm going to make a note. By the inductive step, we know that k plus 2 times k plus 1 factorial is greater than k plus 2 times 2 to the k plus 3. Okay, so let me stop for a minute and explain how do we know that. Well, this right here, I don't like that. Okay. This right here, hopefully you guys can see that. Let's choose red. So what was I doing? This right here is by our inductive step, right? So we can say that from our inductive step because we have that right here. Now, because we can't change anything, we can't just leave that k plus 2 on its own. So as long as we put that k plus 2 on the other side of that, then this inequality here will still hold true. Okay, so that's why that's possible. That inequality, and I don't want that to look like greater than or equal to because it's just strictly greater than. So that holds true. Okay, so hopefully you guys understand that. Okay, because that's sort of the heart of this proof. Once you get there, then it's doing some algebra to manipulate. Okay, so our goal, always keep your goal in mind. Our goal is to have k plus 2 factorial greater than 2 to the k plus 4. So we have k plus 2 factorial. We have the greater than sign, right? So we're doing good. We have k plus 2 factorial equals this, but that's greater than that. So we have k plus 2 is greater than, but now we have to find a way to bring in 2 to the k plus 4. So we have, and I'm sorry, let me take that off. Okay, so we have k plus 2 times 2 to the k plus 3. This is where you have to sort of do some intuitive thinking. We know that k has to be greater than or equal to 5, right? So if that's the case, then the smallest this k plus 2 will ever be is 7, okay? Well, if that's the smallest it will ever be, then this term right here, and let me use a different color. Oh, I'm sorry, hold on. I'll highlight it. Then this term, oh no, that's not a highlighter. I'm sorry. This term right here will be greater than 2. And if I could put it on one line, I would. So if you have room on your paper, put it on one line. I just don't have room on this board that I'm writing on my iPad. So this is greater than 2 times 2 to the k plus 3. Okay. So again, all I did was, well, look at this k plus 2, and I knew from here that k has to be greater than or equal to 5. Well, what am I missing? So think about what you're missing. We're missing an extra 2 here, right? Because when we get here, we know properties of exponents. So this is equal to 2 to the k plus 4. Okay. And actually, yeah, I'll put it because this is true. This is equal to 2 to the k plus 4. Okay. All right. So I could have just, basically what I'm saying is, because I don't want to confuse you guys, but basically all I'm saying is that I can write that as this. Okay. And I would actually probably, if I was doing a proof on my own, I'd probably just write it like that because to clearly show that greater than sign, right? So what we just showed, and maybe, yes, I'll do this. So I'll put it down before we conclude, and then I need to stop this video. But we just said hence k plus 2, and I'm just doing this to show you guys what we did, is greater than, well, equals, of course, k plus 2 times k plus 1 factorial. But that's greater than k plus 2 times, let me erase that, times, I'm sorry, hold on, give me a minute. All right, there we go. K plus 2 times 2 to the k plus 3, and that's going to be greater than 2k plus 4. Okay, so that's what we're saying. I sort of skipped this middle step there, but I wanted you to see that step. And so we can say thus k plus 2 belongs to our set S, and therefore by the GPMI, generalized principle of mathematical induction, S contains all natural numbers greater than or equal to 5. Okay. You could put a little pound at the end. You have room. Okay, so I've went entirely too long because I didn't want to go over 5 minutes, but I didn't want to just stop this video and not finish this proof. So definitely go back over this proof and make sure you understand each step, and I'll talk to you in the next video.